So I'm going to talk about some work that's joint with Guido Sanguinetti, who's my colleague at Edinburgh, who is a Bayesian machine learner, and our joint PhD student, Anastasis Gourgoulas, who finished about 18 months ago and now works at UCL. So first of all, to give you a quick overview, I'll introduce stochastic process algebras. Hopefully most people have seen process algebras before, but perhaps not seen stochastic process algebras. And then talk a little bit about the motivation of why we're trying to bring together this very formal modeling technique with some machine learning and inference, and lead on to the language that we've developed called ProPPA. I'll talk about the inference, show you a couple of examples to demonstrate how it works, and then some conclusions. So a process algebra is a modeling formalism for our purposes that models built as number of agents who engage in actions, and these are basically the primitives of the system, and then we build up our behavior by having these agents working concurrently and interacting in some form. And different process algebras have different ways of imposing those interactions. But in each case, we generally have some kind of structured operational semantics. We're going to be focusing on interleaving semantics, which will give rise to a label transition system, which gives us all the possible behaviors of this system, whatever it is, this set of agents constrained to interact in the way that we like. So that's a classic process algebra in the style of CCS or CSP. And the difference with a stochastic process algebra is that we add in some quantification. So in the classic process algebra, we only talk about what actions can occur. And now we want to know what probability there is of certain actions occurring. And we also assume that those actions have a duration. So there is not just a relative timing of this happens before that, but also some notion of quite how long the actions take. And so we extend with the idea that now our actions become activities that have a duration, and those activities have a rate which is a random variable. Okay, and it's governed by an exponential distribution. And this gives us then both timing and probabilities, because if we have multiple activities that are enabled at the same time, they will each draw a sample for how long they're likely to take using the distribution, and then that will determine a probability of each activity being the one that actually occurs next. And so again, we can generate an interleaving semantics that will give us a continuous time Markov chain. Okay, so these are Markov chains where, again, we have in states a duration before we move on to the next state, and we also have a probability distribution over what that next state will be. And this is generated in just the same way that we define structured operational semantics rules that will give us, in this case, a multi-transition system. We have to take care of how much multiplicity, how many different ways there are of inferring the same transitions. But then once we've got that, we can interpret it quite naturally as a continuous time Markov chain, and we'll generally represent the Markov chain by its infinitesimal generator matrix. So these process algebras originated, first of all, in an area called performance modeling, where we're interested in looking at quantities like throughput or response time of different systems, typically computer systems or communication systems. And so in that case, we get the continuous time Markov chain. We quite often solve it for steady state, so we find a probability distribution of being in any of the states at steady state, and then from that we can derive these measures such as throughput and response time. And so that derivation of the probability distribution can be done numerically using linear algebra or via stochastic simulation. So what do we gain by adding this quantification into the process algebra? Well, the kind of qualitative verification that Jan was talking about can now be complemented with quantification as well. So for example, rather than just asking in a reachability question, is it possible to reach a state, we will ask, how long will it take to reach a state? Now, this is not a deterministic system. We won't get a single answer. We'll get a probability distribution over time telling us how likely it is to reach the state by a particular time. Okay? Similarly, we can look at whether a system matches a specification represented in a logic. And we can look at real model checking, where we have a property phi, and we can say how long is it from a given starting state until the system satisfies that property, or in steady state, what's the probability that this property is satisfied. Okay. So what are the benefits? Well, of integrating Markov chain modeling with a formal language, well, we get properties of the underlying mathematical structure can often be deduced by the language. And so there are cases where we're able to know that our Markov chain has certain properties which might make it amenable to particular types of solution just by looking at the syntax of the process algebra. And then we can, the compositionality obviously gives us benefits in terms of building the models. So rather than having to work directly in terms of states and transitions, we lift this to the components and then have automatic tools generate the whole state space for us. We can use formal reasoning techniques such as equivalence relations and model checking to either manipulate or interrogate our models. And for example, we have a notion of equivalence, which we call Markovian by simulation, which can be applied compositionally, which means that we can then reduce our models in a compositional way, which is something that you really can't do if you work directly with continuous time Markov chains. And we can do stochastic model checking with tools like Prism using continuous stochastic logic. So that's just a little bit of background about stochastic process algebras, and they've as I say, originally were developed for modeling computer systems and communication systems, but in the last sort of 20 years have had many other applications, and one of which is biological systems and systems biology. But actually what I'm going to say applies to many other sort of situations where we have complex systems which are operational, so they're actually behaving and we can collect data from them, but their internal behavior may not be completely transparent to us. So this might be a system that we've designed, but is too complex for us to really know all the parameters. So for example, recently we've been doing some work modeling the London bike sharing system. We know how it works, but we don't know all the parameters there to actually have the full details. But it may be things like systems biology where we really don't know exactly what mechanisms are at play, but we're trying to find that out through modeling and data. So I'll use systems biology and similar systems as an example where we have certain biological phenomena that are observed, and we have wet lab experiments which can collect some data from the system, but not always all of it. But the basic mechanisms and the parameters governing their behavior may not be fully known. But this can apply to many other systems as well that have those kind of characteristics. So the idea of using concurrency in the systems biology kind of context goes back more than 15 years now to a very influential paper from Nature where Rajev and Shapiro pointed out that there was a sort of an analogy that could be taken advantage of thinking of molecules as analogous to concurrent computational processes. And they were the first to suggest that process algebras would be a good way of representing intracellular processes in particular, of various different sorts, metabolism networks or signal transduction networks. And there have been many formal languages developed to take advantage of this. And the formal languages give us a very concrete way of describing the complex behavior and does so in terms of components. So I'm thinking particularly about process algebras and obviously stochastic process algebras, but there are other formal languages that people use, such as Petri nets as well, that have advantages in this domain. So the high-level abstraction makes it easier to write our models and to manipulate them, to do kind of reductions, similar to what Jan was talking about, but not necessarily taking advantage of learning. They can be compiled into executable models, which will then give us a better understanding of the system, and then formal nature lets us do all kinds of analysis and verification. Executing the model gives us data, which we can compare with biological data, but there is a problem that these models need to be fully specified. Okay, so it's a kind of taken for granted that you know everything about your system. So if we're talking about stochastic process algebra, we have to know what actions there are, which components undertake them, and at what rates. And it's typically that last one that we really stumble on. So just to make things concrete, I'm going to give you a very brief, high-level introduction to one of the languages that we use, which is called Bio-PEPA. And this represents things in terms of components, where the components are what are called species in cell biology, which are typically biochemical entities that undertake reactions. Okay, so if we're thinking about the reaction of making a molecule of water, we have 3 different species involved. We have hydrogen, oxygen, and water. Okay. And so those will be our components in the process algebra. In this case, for this process algebra, the local states of the components are quantitative in the sense that what they do is they count how many molecules you have of that species. And a component will vary its space by taking part in interactions, which now naturally we call reactions. Okay, so for the case of forming a molecule of water, we will take 2 molecules of hydrogen, 1 of oxygen, and then we will have a molecule of water. We will decrease the amount of hydrogen by 2, decrease the oxygen by 2, increase the water by 2. So that's the basic modelling paradigm that we're using. And so the effect of the reaction is to vary the parameter of the component by a number which corresponds to the stoichiometry, which is that count of whether you have 1 molecule or 2, or etc., taking part in this reaction. And then we give it a formal semantics. It's slightly more complicated than the general picture I told you of just having a single label transition system. In this case, we have 2 transition relations. The first just tells us what transitions are possible. What are the logical capabilities of these types of species when we put them together? And then we have a stochastic relation, which has to take account of, well, how many molecules are you talking about? What's the rate of this reaction? So we have what we call a capability relation, which just looks at the logical possibilities. If we have these biochemical species that can do these reactions, what are the possible outcomes? And then we have the stochastic relation, which will actually quantify that for us and generate a continuous time Markov chain.
Doesn't the second just subsume the first? Or they're really two?
It's really, they're 2 relations in that you have to have the first before you can do the second, but you need additional information before you can instantiate the function for the second. So there's only really 1 rule in the second, but you need additional parameters. So you can take the same system, and if you change the initial quantity of the different species, you'll get different stochastic out of it. So I'm going to use a simple example that's not actually a biological species. It's a sort of variation on the SIR models. There's susceptible, infected, recovered, but we got a little bored with those, so we changed it around a little. Now, I always say it's innocent, spreaders and repressors. My former PhD student likes to call them ignorance, spreaders and repressors, and it's basically a rumour spreading model. Okay, so the basic idea is that we have some people who are innocent, they don't know the rumour yet, but if they encounter, so this, oh, I can't, so if I point here, these are our innocents. If they encounter a spreader, the rumour is spread, and they become a spreader. They then, if they encounter another spreader, they realise, oh, this is actually old news, and so they may become a repressor, or if they encounter a repressor, they say to them, this is not good, you're spreading this rumour, and again, they will themselves then become a repressor. So in terms of the syntax of the language, it looks like this. Let's ignore these bits at the top for now. These are our species. We have the innocents. They can take part in spread reactions. Just one of them takes part, and afterwards we'll have one less innocent. The spreaders can take part in spread actions, and then we will have one more spreader. And similarly for the 2 stop reactions. We have something here which we call kinetic laws, which tell us the rates at which those reactions will take place. And we're following a law of mass action, which means that the spreading will take place at a base rate, Ks, multiplied by the probability that you actually have these encounters, which is the probability, the number of i's multiplied by the number of s's. So the chances that they bump into each other. And similarly for the other rules. And then in this case, our Ks and our Kr, so the rate of spreading and the rate of repressing, are given concrete values, 0.5 and 0.1. And then we set up the initial state of our system by saying here we start with 10 innocents, 5 spreaders, and no repressors, and then we can just execute this model. So we generate the underlying CTMC and perhaps run a simulation, and we see how the rumour spreads through the population. Okay, and as we alter the parameters, we would see different patterns of spread. So I posed earlier the question of what happens if we don't know all those rates. So what if we don't know Kr and Ks? What happens in practice is quite often that we try and parameterize the model through some kind of iterative approach, possibly manual, where we will simulate, generate data, update, compare that with our experimental data, the data that comes out of the system that's actually working, and then use that to update our model and so on to try and optimize so that we've got a good representation of the phenomenon. But there is, of course, an alternative. The model creation instead can be data-driven. So we start with the data and represent belief and uncertainty as probability distributions. We're talking about a Bayesian representation. And then treat parameters and unobserved variables in a similar way and use Bayes' theorem to try and update our beliefs about the system. So we have some kind of prior knowledge that we believe about what the rates might be. And then we have evidence from running our model, and then we can say how that helps us update our belief about those parameters. So these two approaches are often seen as, in some ways, competitive. And so we have the approach of machine learning where we extract the model from data generated from the system, or we have some notion of a model that's refined through statistical techniques, whereas the formal approach is much more of a mechanistic model where we start from a descriptional hypothesis about the system and algorithmically mimic the behavior of the system to generate data. And they have distinct advantages and disadvantages, and I think mine are similar but not quite the same as the ones that Jan had. So in this context, we say that the data-driven modeling is much better at handling parameter uncertainty. It's really built in that the whole idea is that you have these distributions about the parameter uncertainty. But the framework's not really been set up to deal with stochastic models so well. Okay, and there's a lot of difficulty in actually applying many of the standard techniques to CTMCs. And in many cases, bespoke solutions are needed in order to carry out inference, and it's limited by the size of system that you consider. In contrast, the mechanistic model, a lot of the focus has been on building this generic engine, if you like, that can be reused for many models. And this is really what the language is. The language gives us an engine that you can give any model in that language. You've got a way of constructing the underlying CTMC, and then you've got an engine that executes that CTMC and lets you derive things about your description. So we have that much more general purpose sense to the technique that we use. The models can be used speculatively, so we can make changes to our hypothesis to investigate the role of parameters or parts of the system by changing them where we don't have data. But the parameters are assumed to be known and fixed, or we have these quite costly approaches to seek appropriate parameterization. So what we wanted to know was there a way of putting these two together to get the benefits of both, so that we could include information about the uncertainty into a formal model, automatically use observations to refine that uncertainty and do it in this formal context, which gives us a notion of being able to have a general engine and not having to make a bespoke solution every time we want to do this. And so this led to the work of Anastasis's PhD, which was a new language called ProPPA, which is probabilistic programming process algebra, which is really quite a small extension of Bio-PEPA, as we'll see, to include those elements that are currently missing. So I'm sure most people here are familiar with probabilistic programming more than I do, but it's always difficult when you're talking to a general audience, so I'll just quickly go through. So it's a programming paradigm for describing incomplete knowledge scenarios and resolving uncertainty. And the programs themselves are high-level languages that look like software code but have the probabilistic elements that we saw earlier this afternoon with Luke, with the idea of having random variables as a first-class object in your language. So these offer automated inference without the need to write bespoke solutions, so similar to what we wanted. And types of platforms I'm thinking about are things like IBAL, Church, Infer.net, Fun, Anglican, Web PPL. There's a lot of them out there. And the key actions are that you would specify a distribution, specify some observations, and then infer the posterior distribution that comes from that. So generally what we would do as a workflow here was describe how the data is generated. So our probabilistic programs are generative. And the syntax is very much like a conventional programming language, but with some variables left uncertain and specified as random variables. We specify some observations which will impose constraints on what are acceptable outputs from the program. And then we can run it forwards and generate data that's consistent with the observations, or we can run it backwards to find values for the uncertain variables that are consistent with the observations. Okay, so this is a general sort of probabilistic programming workflow, and we wanted to extend that to the context of Markov chains. Why is that a little bit harder? Well, because our Markov chains don't have a given output, even with the same variables, because they are inherently stochastic, a bit like me, and so they can generate different outcomes every time you run it. So you've got another level of uncertainty and probabilities there on top of probabilistic programming. So this was our objective in developing ProPPA, was to keep those features of the stochastic process algebra which were good. So it was easy to describe things in terms of components, and then we have this engine from the semantics that give us an executable model, but then incorporate into the language those features from probabilistic programming of recording the uncertainty, and for the moment we're focusing just on parameter uncertainty, have some way of recording the observations and building those in, and then accessing inference to update the uncertainty. So in terms of our small example, this was how it looked before. So everything here is nailed down, and in particular we have these fixed values 0.5 and 0.1 for the rates of spreading and repressing. But instead now we want to change this to have some uncertainty. So for this simple example, I'm just going to say the rates there are just uniform between 0 and 1, so I know nothing except they fall between the values of 0 and 1. I can provide some observations in terms of a trace file, so a few data points like a time series that we might get from a biological experiment, and I can specify an inference approach. And in this case, I'm just going to talk about very simple inference in terms of approximate Bayesian computation. And so this is now a proper program or a proper model because we have incorporated uncertainty in the parameters, which observations we're using, and then how we're going to infer. So the semantics is just really extended from the Bio-PEPA semantics. But there's a difficulty because Bio-PEPA gave us a CTMC, a continuous time Markov chain, which has to be fully specified. There cannot be any uncertainty there. So every transition must have a concrete rate, and the whole point was that we don't have that. So we needed to find some other mathematical structure that gives us something a bit more like a distribution over continuous time Markov chains as the mathematical object of our model instead of a single CTMC. So if we have a concrete value, we would get a single CTMC. With a set of values, we would have a set, and here we will get a distribution over the CTMCs. It's not quite so straightforward because we may have several parameters there with different distributions, but you can see how it works. So we looked around in the literature to see if somebody had done this before. It seemed like maybe somebody would have done. The closest we found was constraint Markov chains, which are a generalization of DTMC, deterministic time Markov chains, in which transition probabilities are not concrete, but are subject to some constraints. And these are generalization themselves of interval Markov chains, where you just have an interval for the probabilities, but these allow more compositionality by extending that to constraints. So we have a set of states and an initial state, a set of atomic propositions, which are really for reasoning about, and then labelings on those. And then here, where we might expect to have a rate function, we have a constraint function that tells us acceptable, or in this case, probabilities for each of the possible transitions within our model. So in this case, the arbitrary constraints are permitted, and it's just a Boolean acceptance vector. So either this is an allowable case or not, whereas we would like to have something that gives us a distribution. And it's also just the discrete time case, so it's just looking at probabilities where we want to look at rates. So essentially, we want to take this case where they're just saying, OK, it's acceptable for me that it's in 0 to 5, and we want to impose a distribution on that. So it's simple to extend it. We call it a probabilistic constraint Markov chain. So the states, initial state and atomic propositions and acceptable labelings are all the same, and the difference is only in our constraint function, which now, instead of being 0, 1, of just being a Boolean condition, is this a transition you can make or not, we now have arbitrary rates, and the actual value of the transition from a particular state is a probability density function of the governed by the distribution that you have. So now for the semantics of ProPPA, the capability relation stays exactly the same, because the logical properties that we can, or the logical reactions that we can undertake, are the same as they were with the Bio-PEPA. But now our stochastic relation, instead of giving a rate, will give us a distribution of rates on the transition. And we express this in terms of state-to-function transition systems rather than just state-to-state transitions. And this will give rise to an underlying probabilistic constraint Markov chain. Now, when we come to interpret those, I talked about the models being executable. There's two alternative interpretations that we can make on such mathematical structures. The first is what we call an uncertain Markov chain, which takes the view that in some sense there is a real value somewhere in that distribution. And so as you want to execute this model, you want to generate a trajectory, you sample from the distribution, you keep that value throughout the whole model. So in other words, you just take the one CTMC and you execute it. And then the next time you want to do a trajectory, you sample again. The other, which we call imprecise Markov chains, assumes that the rate is uncertain because it may be subject to elements that you're not modeling in your system. So it may actually vary during the execution. Okay, so in this case, each time you encounter a transition with that rate during the execution, you resample, and you would get a possibly different value over time. For the moment, in this work, we're focusing just on uncertain Markov chains. Okay, so we have our model with the distributions within it, which gives us a distribution of CTMCs, and we want to incorporate observations and carry out inference to generate a posterior distribution, the general framework that everyone uses, but it's just a little bit more complicated because we're dealing with CTMCs and possibly infinite state CTMCs. So exact inference isn't possible. because we cannot therefore calculate the likelihood exactly. So we use various different approximate algorithms or approximations of the system. I'm not going to talk very much about the inference today, but just to say that what we aim to do here is to have a modular approach that you can plug in different inference algorithms with the model according to certain characteristics of the model. So different algorithms can act on different inputs. All the examples I'm going to show you today, the observations that we embed in our inference are going to be time series, so we assume that we have some data recorded over time that corresponds to trajectories, but we do also sometimes work with logical properties. So we also have some inference algorithms that work where we can express a property in continuous stochastic logic and then see how that affects the posterior distribution. So the key thing about our states is usually the probability in being in each of the states at different times. Okay, so with the performance modeling, we're often looking at steady states, so we're looking at infinite time. With the biology, we're typically looking at a given time. So this is the, well, it has many different names. To me, it's a Chapman-Kolmogorov equation, but it's telling you how the probability of being in state I changes over time according to the transition rates in and out of that state. And so the probability of a particular observation of seeing y at time t can then be expressed as the sum over all states, so the probability that we're in state I and that y is observed in I, and we sum over all states. And then the likelihood can be expressed as this version here, where we're now looking at those probabilities, the probability of being in state I given a particular parameterization theta. So for finite state spaces, the transition probabilities can be computed through an equation like this one, or via techniques such as uniformization. Computation can be expensive if the state space is large. That means that the matrix Q is extremely large. And this obviously becomes impossible if the state space is infinite because we cannot construct Q. So there are alternatives, the most simple of which is approximate Bayesian computation, which I'll rehearse for my benefit, but probably not for yours, which assumes that we can build an approximate posterior distribution from a set of samples, and the likelihood of parameters is approximated with a notion of distance. So if these are our observations, we can choose a sample from our distribution of CTMCs, pick one CTMC, get one trajectory. It may have many possible trajectories, but we get one trajectory. And we look at the distance between our time series and that trajectory, and then we can accept or reject. In this case, it looks likely we will reject based on the distance, whereas another trajectory from another CTMC within our distribution would give us a much closer match, and we would accept that. So essentially, we run many, many simulations. So we've got a distribution of CTMCs. We sample to get a concrete CTMC, and then we run that. But we will do that many times because each time we run that, we may get a different answer as well. So it's computationally very expensive, but conceptually extremely simple. Okay, so this is essentially the kind of base case that works for all our models. But we try to avoid it. We have, as I say, other inference algorithms as well. But we sample a parameter set from the prior distribution, simulate using these, and then collect data when we get something that's acceptable. And this will then give us an approximation of the posterior distribution. But in the case where we have infinite state spaces, as I said, we cannot do that, and there's various different ways that people have looked at that. We've also looked at linear noise approximation, and we have inference algorithms within our toolset that does linear noise, but the most novel that we've done is a random truncation. So now we can look at our likelihood as being expanded in terms of the probability of moving between two states. So we're looking at the probability of having been in state x at time t. What's the probability that we're in state x prime at time t prime? And we can express that as a sum, where we're summing over this value n, where n is some notion of how long your path is. How far are you going from where you started? So we have an infinite state space, so this infinite sum will cover all our cases, but it's a way of splitting those probabilities in terms of the trajectories and how far they're going. And then we can reorganize this to look in this more convenient form, but it's really, we're just looking at the cases where the maximum state cannot exceed this value x star plus n. And then we use what's called a Russian roulette truncation to actually estimate this infinite sum with a random truncation. And so we don't need to explore the whole state space. We just look at some truncation, which is then something we can do, and we can then apply usually a Gibbs sampling. So just to give you an idea, these are our states where we're starting. Then the zero case, this is the kind of maximum where we're keeping this population of a maximum of 2 here and 1 there. If we allow to go 1 greater than that, we get these states and so on. So this is the way that we're building up our state space, and we do a random truncation of deciding how far we go with that. Okay, so just quickly to show you some results. This is our rumor spreading example again. We tested this with 2 uniform priors, as we saw in the case before, that we just assumed that they're between 0 and 1, and we used approximate Bayesian computation. The observations that we used were a time series from a single simulation run. So this was our prior, and then this is our posterior approximated by ABC, and the red line shows the true values that generated the one simulation run that we used as our observations. Okay. So what you can see here is actually we're getting quite good results with respect to, which one is that, KR. But it doesn't seem that we're doing so well with KS. But it is quite sharp, this end here. And we investigated this a lot further, and what we found was that the model is quite insensitive to the value of KS as long as it's bigger than 0.2. If it's less than 0.2, the rumor really doesn't spread, it just dies out very quickly. But above that, it doesn't make a lot of difference, which is why we have that quite wide distribution. To show you a more realistic biological example, we have an example which is 2 mutually repressing genes. So there's promoters, which are unobserved, and protein products, and we get a bistable behavior because one gene, when switched on, produces a protein which represses the other gene, and so on. And this is a system that has been synthesized in E. coli, and there is a stochastic variant model that was developed by Burridge and collaborators. So this is the basic idea. We have our genes. Gene 1, is when it's switched on, will produce protein 1, which will degrade over time, but while it is there, it enhances the switching off of gene 2, but meanwhile, when gene 2 is on, it produces protein 2, which switches off gene 1. So we expect to see oscillations of protein 1 and protein 2 in our system. So the model looks like this. We can see that the genes are activated, deactivated, and then promote the expression of the genes. Sorry, those are the genes, and then the proteins, and etc. And we start with a system where we have gene 1 switched on, gene 2 switched off, and 20 molecules of protein 1. In this case, we have some observations, and we're using our Russian roulette version of Gibbs sampling. This is the fuller stuff, and we've got these parameters, theta 1 to theta 8, and these are what we're trying to find. So we simulated observations based on, again, running a simulation with the true values of these parameters. We assume that they have gamma priors, which is required for the algorithm, and we seek to learn those 8 parameters. And we use 5,000 samples of the Gibbs algorithm, from the Gibbs algorithm. So these are the genes from the one simulation trace that we generated, but these are unobserved. We don't give this data to the model. But these are the proteins that come from those genes switching on and off, and we just sample 20 points from each of those trajectories. So this is the data that we actually give to the model for the inference. And then I'll just show you the first 4 of the parameters θ1 to θ4. In each case, the dotted line is the prior, the red line is the true value, and the dark blue is the posterior that we infer. And you can see that the results are pretty good in most cases. Okay, so this is our sort of workflow. We assume that we have some kind of model that we can compile into a low-level description, which for us is this probabilistic constraint Markov chain. And we have an inference algorithm and some data, which we can then infer some inference results and carry out normal things that you do when you're doing systems biology modeling. So ProPPA is a process algebra that incorporates the uncertainty and observations, but retains syntax that's quite close to Bio-PEPA, which is quite good from our point of view because we have users for Bio-PEPA and now some of them are adopting ProPPA as well. The semantics are defined in terms of this extension of constraint Markov chains to probabilistic constraint Markov chains, and our observations can be either time series or logical properties. And we have various inference algorithms that we've developed as well. So thinking in terms of future behaviour and how to try and get a playoff between this inference and the formal setting, one of the ideas that we're interested in investigating is if we update to our posterior distribution, is there some way that we can reason about the distance between the prior and the posterior that gives us a measure of the value of those particular observations? And another one is we've been assuming that there is a true value of the parameters, and we're seeking for a posterior that narrows towards that true value. But what if instead what we want is some kind of heterogeneous population where we're looking for the optimal mix, that we have many copies of the same kind of process, and what we're looking for is the right balance to achieve something at a global level through their interaction. So those are 2 ideas that we're currently pursuing. I'd like to thank my co-authors, Anastasis and Guido. Anastasis will be here part of the day tomorrow, but unfortunately is still in Greece today. And our funders, which was Guido's ERC grant, Microsoft supported Anastasis, and I've been funded by the CEC. Thank you.